Hello everyone and welcome to my channel where we solve math and physics problems just for fun. Today I decided to take a look at 4 problems from some randomly chosen Chinese Math Olympiad. I think this one is from 2002. So here are the problems. Let's start with problem number 1. So in this problem, we're supposed to find all positive integers n such that the following polynomial expression is a perfect square. Okay, let's start by introducing an integer number m such that this thing is m squared. So we want to solve such an equation on n and m. Positive integers. Well, n is a positive integer. M in principle can be any integer, but we can assume that it's a non-negative. So m, non-negative integer, which can be done without loss of generality. Okay. Let's play with this expression a little bit. So the first thing I notice is that this part, the first two terms, kind of look like like they're trying to organize themselves into a perfect square. What I mean is that I can write n to the fourth minus 4n cubed as n to the fourth minus 4n cubed plus 4n squared minus 4n squared, which in turn becomes n squared minus 2n squared minus 4n squared. Okay. Let's see if it's useful. Our equation is then, if I use this and put it into the equation, we get n squared minus 2n squared minus 4 plus 22, so plus 18n squared minus 36n plus 18 minus m squared equals 0. Okay, now, look, we get n squared minus 2n here, and there's something similar going on here, namely n squared minus 2n squared plus 18 n squared minus minus 2n right, plus 18 minus m squared equals 0. Now we have the same n squared minus 2n here and here. So again, it looks like these two terms are trying to organize themselves into a perfect square, which is n squared minus 2n plus 9 squared. But now we need to subtract the extra 9 squared that we added. Then we have plus 18 and minus m squared equals 0. Okay, so here we have a square minus another square. So I'm gonna rewrite this in the following fashion: n squared minus 2n plus 9 minus m times n squared minus 2n plus 9 plus m, and this equals 81 minus 18, which is 63. Perfect. Now we can just look at this expression, and we notice that well, all we need to do is factorize 63 into a product of two integers. And furthermore, they are obviously positive, right? Because this one, maybe I'll write it here, that in this little box, that n squared minus 2n plus 9 equals n minus 1 squared plus 8, so it's strictly positive. Now we know that m is greater or equal than 0, so this whole thing is strictly positive. Therefore, because the product is 63, which is strictly positive, this is also must be strictly positive. Furthermore, this first expression is definitely is strictly less than this one. So it's a smaller number. This one is a smaller number. Therefore, let's just factorize 63 into the product of two integers, two positive integers, such that the first one is smaller. So what are the options? Well, there are, I guess the first one is 1 times 63. Another is, well, let me write 63 as, it's 7 times 9, right? So it's 3 times 3 times 7. So it's 1 times 63, or 3 times 21, or 7 times 9. Yeah, there are only 3 options. 1, 2, and 3. So in the first case, oh yeah, and we should notice that we can, so we have sort of, now we have a system of two equations, that this one equals 1, this one equals 63 in the first case. In the second case, this is 3 and this is 21. And in the third case, it's 7 and 9, right? Furthermore, we can add these two expressions, and the m will cancel when we add them. Okay, so let me write this in slightly more detail first. The first case. In the first case, we have these equations. Let me write it like this: n minus 1 squared plus 8 minus m equals 1. N minus 1 squared plus 8 plus m equals 63. We take the sum, and this gives us 2n minus 1 squared plus 16 equals 64. In other words, well, 64 minus 16 is 48. 48 divided by 2 is 24, so we get that n minus 1 squared is 24. This clearly has no integer solutions because 24 is not a perfect square. All right, here we have no solutions. Now, if we repeat the same, let's repeat the same for the second case. Here, by doing the same steps, we get the equation 2n minus 1 squared plus 16 equals 3 plus 21, right? 3 plus 21, which is 24. Therefore, n minus 1 squared equals 24 minus 16 is 8, divided by 2 is 4. Okay, n minus 1 squared is a perfect square, 4. So n minus 1 is plus minus 2. But because n is a strictly positive integer, it means that n minus 1 is 2. So there's only one solution. We get n equals 3 in this case. Now let's look at the final case, and hopefully I'll be able to fit everything into this one page. Okay, in this case, the same equation gives us 2n minus 1 squared plus 16 equals 7 plus 9, which is 16. So n minus 1 squared is 0. Yay! Another integer solution. N equals 1. Okay. So we get two candidates for solutions, n equals 1 and n equals 3, but then it's clear from these equations that m will be an integer too, automatically, because m, for example, from here is just an integer expressed in terms of this, just by saying that this whole expression is either 3 or 7, right? So yeah, we found our solutions. There are only two solutions, n equals 1 and n equals 3, and you can actually go back to the first equation and check that indeed they give you perfect squares. Okay, let me just highlight the answer I guess I'll do it in green. Answer is n equals 1 or n equals 3. There are two solutions. Great, let's move to the next problem. So here's the second problem. Again, you can pause the video, take your time to read the problem. It's the geometry problem. Okay, so there's an acute triangle ABC. Here it is. It has a circumcenter O. Okay, it's kind of a small picture. Let me draw a bigger one. Draw a triangle here. Okay, and then the circumcenter will be no, I didn't draw a good triangle. This looks like the right angle, but we need an acute triangle. So I should draw it like this. This is better. So here's the circumcenter, which means that these three lines connecting to the vertices of our triangle have equal length. So the vertices are A, B, C, and O in the center. Okay. P is a point inside AOB. Okay, so the problem says that inside this triangle, we pick a point P and we project P on the three sides like this. So this is another projection. Here's another projection and one more projection. Okay, so these projections are actually, let me do it in green. These are right angles. Another right angle. So the problem is asking us to look at this. These two segments and continue them to a parallelogram, which means that, actually, let me write the names for these vertices. Like on the smaller picture, this is E, this is F, this is D. And then we draw another segment which is parallel to FD. Like this. And one more segment that is parallel to FE. We get a point, well, it's called G on the original picture, so let us use the same name. So the problem is asking to prove that the parallelogram that we just drew lies inside the big triangle ABC. What does it mean? These two segments are automatically inside the triangle. So what it really means is that this part remains inside the triangle. So in other words, there's something like this doesn't happen, right? So in order to prove that, we need to prove that this angle here is strictly positive. How do we prove that? Let's see. Somehow it is important that the point P is inside this triangle. So what happens if, instead of looking at point, well, if I move it close to the boundary of this triangle, let's say I move it to this point, or to this point, or to this point. Well, okay, if I move it close to this point, then the projection will look like this, and this projection will look like this. And then clearly that the line that's parallel to this line will have, well, it will just go down vertically. So necessarily this angle will be positive, because in order for it to be negative, this side would have to be like at this angle, like I would have to have a triangle, something like this, which is not an acute triangle. So, okay. So point at this boundary works. Now, what if I take point P to this boundary of let's say here? Let me draw this actually on a separate picture. Let me draw one more picture. So one more triangle. I kind of make it slightly bigger. And I want to do it in blue color like this. No, I want it bigger. Bigger is better. This is the case where the size matters. Say that this is our O, roughly. Okay, fine. So let me introduce names for the vertices. C, A, B, I will also, like this point, I'll call it Q. Huh? So now I will introduce point Q here. And then there are projections. And actually, I will not look at the third projection. I think, yeah, I want to look at this one first. And then we have this segment. Well, okay, maybe I'll draw the other projection as well. I mean, let's say that it's somehow like this. And so we'll have also another segment here. But no, let me not overload the picture. What I want to do now is perhaps, yeah, let me move also this, not to overload the picture. What I want to check is whether this segment is parallel to AC. Why do I think it might be parallel? And why do I think it will help? Well, because if it's parallel, then once I take point P here inside the triangle and do the same procedure of projecting here, then the new segment will be at a certain angle, positive angle compared to the orange line, and then the parallel segment here will be at the same positive angle relative to AC, and then this will prove what we need to prove. So for now, we just need to show that this orange segment is parallel to AC. How do we do that? How do we do that? Okay, let me also introduce back the names. F, D. Let's also call this angle alpha. This angle will also be alpha because, since O is the circumcenter, it means that this and this and this have the same length. Therefore, this angle equals this angle, and then this angle equals this angle, and this equals this. So let me introduce also names beta for this angle and gamma for this one. And because the sum of three angles in any triangle is 180 degrees, it means that automatically alpha plus beta plus gamma is 90 degrees. Maybe this will be helpful. Now let me also, I see what to do. Let me call this angle, this one X, and this one Y. Okay, so this is X. It's too small, sorry. Let me do it like this. This one, and this one is X. This one is Y. Also, because this is right angle and this is right angle, it means that the sum of these two angles is 180 degrees, which means that this angle is 180. Let me use slightly thinner pen, thinner brush, thinner pen. 180 minus alpha minus gamma. Okay, it's for this angle. Okay, now let's use the theorem of sines. And in principle, once you have this picture, and if you remember any kind of high school geometry or maybe middle school geometry, then, or if you ever competed, you would immediately recognize that actually x equals gamma and y equals alpha. But strictly speaking, we need to prove that. Let's prove it. For that, I will use the theorem of sines, or whatever is the proper name for it. I don't remember. But I will use it several times for different triangles. For this triangle, for this triangle, for this triangle. Maybe there's a better way to prove it, but a proof is a proof, whatever works. So let me write it like this. Actually, let me move this a little bit. This expression is what I want to prove. I want to prove this. And now let me prove it. For that, I write first sine x divided by the length of dq equals sine of this angle, which is sine of 180 minus alpha minus gamma, which is the same as sine alpha plus gamma. All right, because remember that sine 180 minus alpha is the same as sine alpha. So I'm just using this property. So this divided by the length of FD. But now I may use the sine theorem for this triangle, because now this one is also this angle. So sine of this angle over FD equals sine of this angle, sine of this angle divided by BD. But sine of this angle is actually cosine of x, because together they form the right angle. So now I got cosine of x divided by the length of BD but BD and DQ are actually related by the tan of gamma, right? We get that cosine x, that BD is actually, what is it? Is DQ divided by tan gamma, right? Because tan gamma is DQ divided by BD. So we get that DQ over tan gamma is BD. Awesome. Now we have this equal to this. We can just get rid of DQ, and we get the following equation, that basically tan x equals tan gamma. Now we know that gamma is positive, but it's less than 90 degrees. In fact, it's even less than 45 degrees, but what matters is that it's less than 90 degrees. Same x is positive, is less than 90 degrees. In this region, here, tan x is a monotone. It's a monotone function. It means that it increases as you increase the argument of your function. One second. Do I even need to say that it's monotone? It's a monotone function? Yeah, well, I need to say that the inverse function exists. So I can conclude that x equals gamma. All right, but now what we have that since x equals gamma, then let me use the red color. And it means that this angle here is 90 degrees plus x, or plus gamma. This one here is alpha plus beta. So the total of these two angles, this and this, is, let me write it in this sort of, this, I think that this is the notation that we used in high school. Angle BAC plus angle DFA equals alpha plus beta plus gamma plus 90. But we know that alpha, beta, gamma sum up to 90. So we get that this is actually 180 degrees. Okay, what does it mean? When you have a line, another line, sorry, this line, another line, and they are intersected like by something like this, and the sum of these two angles is 180 degrees, it means that these two lines are parallel to each other. All right, so we proved that FD is parallel to AC. Therefore, this actually proves what we wanted, because now, if I consider a point P in sight, which sits here, just above the point Q, and start projecting this point, then I get what we needed. Then I get that this angle here is strictly positive, and then you can use the same argument to prove that this angle is strictly positive, and then we're done. Okay, this problem solved. Let's move to the third one. Okay, you can pause to read the problem if you want to. Here we consider a square on the complex plane. Square on the complex plane. The complex numbers corresponding to its four vertices are the four roots of some equation of the fourth degree with one unknown and integer coefficients PQRS. Find the minimum value of the area of such a square. Okay, so let's draw the square. So it's a square. Complex plane, so it has vertices. Let's call them Z1, Z2, Z3, Z4, and they are roots of some fourth degree equation. Well, of course we can write the equation always like this: product of Z minus Z1 times Z minus Z2, Z minus Z3, Z minus Z4 equals 0. But perhaps it's not the most useful way to write it. Let's see. Well, since they're all on the if I consider all these relative to the center, let me say that this is the center of our square. It's called A. Then Zi minus A, they all have the same length but different angle. And in fact, the phase, different phase. And in fact, their phases differ by by 90 degrees. Okay, so if I consider Zi minus A to the fourth power, then this difference in phases will disappear. Okay, so then it means that the equation actually, that they are satisfying. is, let me write it in red. The equation is like this: x minus a to the fourth power equals some number r, rho, w, some complex number w. And now we know that x to the fourth minus 4a x cubed plus 4 choose 2 is 6a squared x squared minus 4a cubed x plus a to the fourth minus w equals 0. And according to our problem, all these coefficients are integers. Okay, 4a is integer, 6a squared, 4a cubed, they're all integers. What does it mean? I think it means that a is itself an integer, right? For a cubed is 4a times a squared. This is an integer, for a cubed is an integer, for a is an integer. Can a squared be not an integer? Can it be a rational number? I had to change music because the previous one ended. Okay. If a squared is not an integer, then it's a rational number. Then a itself is a rational number also. So a is a rational number such that 4a is an integer and 4a cubed is an integer. Huh, that's weird. So let's say that a is rational. Okay, if a is p over q, but 4a is an integer, this means that q is even. So let's write it actually as a over 2q at least. Right? Because only that multiplying by something like 4 will give you an integer, but then 4a cubed will be p cubed over 2q cubed. And the only way for it to be an integer look, if p over 2q is, look, if this was a rational number, it means that p is odd. But then this is also a rational number. But it must be an integer. Impossible. Well, it means that this was actually an integer. Okay. Great. We conclude that a is an integer. But then looking at this part, we see that also w is an integer. So we simply have an equation of the form x minus, well, okay, we already have the equation written here. This equation where a and w are integers. Well, now we can, let's actually simply shift. We can shift this equation to the origin such that a is 0. Shift. It's an integer shift, so it's not going to affect much. Now the new equation is x to the 4th equals, let's say w. Sorry, I shifted x, so I have a new x now. Actually, I will call it y, which is x minus a. And the equation now is y to the 4th equals w, where w is an integer. Well, then we're done, basically, because if we draw the complex plane, then solutions to such equation, basically, they are here, like this, where we have the 4th root of w here, and then keep switching into the eraser. Here we have 4th root of w times I, minus 4th root of w, minus 4th root of w times I. And if we want to minimize the area of this square, then clearly we should take the minimal positive w. That is w equals 1, in which case the length here is square root of 2, and the area is square root of 2 squared equals 2. Yeah, this is our answer. This is the minimum value of the area. Okay, third problem done. Now let's look at the fourth problem. Ready? So in the fourth problem, we have a positive integer n, and we have a collection of n plus 1 non-empty sets. And these are the subsets of the set of integers from 1 to n, okay? Prove that there are 2 disjoint and non-empty subsets. Subsets, I guess, of the same set. Subsets such that A's indexed by the first subset, you take the union, is the same as A's indexed by the second subset, and you take the union. Okay, so we have n indices and elements, but we have n plus 1 subsets. Let me actually do the following. Let me use some linear algebra. I will characterize the subset of this set by a collection of n numbers, by ordered collection of n numbers, which are the zeros or ones. It's 0. Let me say that. For a subset, if we have a subset A equals collection of I1, Ik inside 1, 2, n, then I will say that I will introduce an n-tuple or a vector VA is a collection of zeros and ones such that, actually not just a set, it's an ordered collection such that on the ith position I have either 1 or 0. 1 in case I belongs to A, and 0 in case I is not in A. What does it mean? Well, it means that it's kind of like an indicator set. Here, 1 on the ith on the position number I, or the position number K, or whatever. No, I should use different number. Position number P here has 1 if element P is in the set, and it's 0 if position number P is 0 if element P is not in the set. For example, if A is just 1 and 3, then corresponding VA will be 1 because there's 1, 0 because 2 is not here, 3, 1 on the third position because 3 is here, and then the rest are just zeros. Cool. Next we all right, so we have n plus 1 such subsets. Therefore we have n plus 1 vectors. N plus 1 vectors VA1 VAN plus 1. Yeah, because VA is a collection of n numbers, so I think of it as a vector. A vector in what space? Well, there are n numbers, so it's actually in Rn. All right, but now it's clear what to do. We have n plus 1 vectors in Rn, so they are necessarily linearly dependent. It means that there exists some linear combination. Bad choice of letter. K. From 1 to n. CK V AK, which is 0, where not all CK are 0. So some CKs are necessarily non-vanishing. So now let's collect the positive CKs on the left and the negative CKs on the right. So we get the following equation. Sum K from the positive set of positive CK. But I think you understand what I mean. And here we have sum over K such that CK is negative. And so since we moved it to the right, it's minus CK. So minus CK becomes positive again. VAK. And let me actually use a different letter here for the index, just to emphasize that this is a different set of indices. On the left we have indices that are positive, on the right we have indices that are negative. Let's call them J. So these are strictly disjoint sets of indices. There are some indices have positive ck, some indices k are such that ck is positive, and some indices j are such that cj is negative. Right? So these are disjoint sets of indices. But then it means that basically what I want to say is that this sets satisfy this equation. Indeed. If some number from this collection, some number p, appears in these sets, it means that on the p's position in some of these sets, we have one, and it's multiplied by some positive coefficients on the left. But then on the right, we need to have also 1 on the p's position in some vectors, and then it's multiplied by positive coefficients, such that the left and right side match, right? In order for the left and right side match, they need to be, this total sum need to be the same vectors, so they need to have the same non-zero entries. What it means is that whenever number p from this collection appears on the left, it also, among these sets on the left, it also appears on the right, and vice versa. And basically we get to that the union over k, maybe I'll write it better, such that ck is strictly positive, the union of ak's is actually equal to the union of j's such that cj is negative over aj. All right, there you go. We proved. We solved the problem 4. Yay. That's it for today. I hope you enjoyed it or found it educational. Next time we select some other problems from some other competition. Maybe it will be physics, maybe it will be math. I'll decide basically based on my mood or maybe on your comments. If you request something in the comments, then I'll try to accommodate that request. For now, that's it. Thank you and see you next time.